Welcome to a new part of our lecture series on wind turbine modeling. In this section, we will present the electrical equations of the permanent magnet synchronous generator. The following table provides the values and descriptions of the parameters and variables used in this section. The stator voltage, stator flux linkage, and electrical torque of a synchronous machine can be described by the following per-unit equations. Figure 23 shows a schematic diagram of the stator and rotor circuits of a synchronous machine. The derivation of these equations is beyond the scope of this presentation and can be found in books on electrical machines. For this study, the equations of the synchronous machine are simplified because the permanent magnet synchronous generator does not have damper windings and has a constant field flux. With these simplifications, the stator flux linkage equations are reduced to equations 76 and 77. Substituting the D and Q axis stator currents into the stator voltage equations yields the stator current dynamics shown in equations 78 and 79, while the electrical torque results in equation 80. These equations will be used to model the dynamics of the permanent magnet synchronous generator.
Now, we will describe the back-to-back converter model. This table presents the nomenclature used in this section. Figure 24 shows the detailed switched model of the grid-side converter. This model allows the study of pulse width modulation techniques, harmonics, and the dead time effect. However, it requires small simulation time steps to accurately represent pulse width modulation pulses. Since this lecture does not focus on pulse width modulation or harmonic aspects, we will use the average model of the converter to reduce the computational load. Deriving the average model from the switched model is beyond the scope of this presentation. Figure 25 shows the AC and DC circuits of the average model. These circuits will be used to derive the converter dynamic equations.
Now we will describe the dynamics of the AC current in the grid-side converter. By applying Kirchhoff's second law to the AC side circuit of the average converter model, we obtain equation 81 in the stationary ABC reference frame. This equation uses vector notation and the International System of Units. We can also express this dynamics in the stationary 0 alpha beta reference frame using the Clark transformation. In this study, we assume a balanced three-phase system. Therefore, there is no zero sequence component, and the dynamic equations can be simplified using complex notation. For example, AC current dynamics in the stationary alpha-beta reference frame is reduced to equation 83, whereas in the synchronous DQ reference frame, it results in equation 84. Next, we will describe a procedure to derive equation 84 from equation 83. Traditional approaches using vector or complex notation can be applied to convert equations from the alpha-beta frame to the DQ frame, as seen in equations 44 and 46 derived in section 5. As an alternative, we show here how to convert equation 83 from the alpha-beta frame to the DQ frame using the frequency translation approach. First, replace the derivative operator with the variable s. Then perform frequency translation by replacing s with s plus j omega s. Finally, isolate s on the left side and replace it with the derivative operator to obtain equation 85.
Now, we will show how to convert equation 85 from the International System of Units to the per-unit system. First, divide equation 85 by the base voltage. Depending on the term, the base voltage is written in different ways using the base quantities introduced in the per-unit system section. Next, define the per-unit variables and parameters by identifying those divided by their corresponding base values. Here, variables and parameters in per unit are denoted by a bar. The nominal angular frequency of the AC grid is used as base frequency. Finally, by separating the real and imaginary parts of equation 86, we obtain equations 87 and 88. These equations model the AC current dynamics of the grid-side converter. They are in scalar form and in per unit. In this model, the D and Q axes variables are constants, which simplifies control design and equilibrium point and eigenvalue calculations.
Now we will describe the DC voltage dynamics. By applying Kirchhoff's first law to the DC bus node, we obtain the following equation in the stationary ABC reference frame. This equation uses vector notation and is in the International System of Units. Using Clark and Park transformations, we can express equation 89 in the alpha-beta and dq reference frames, respectively. Using the same methodology as before, we can convert the DC voltage dynamics from the international system of units to the per-unit system. Assuming a balanced three-phase system, the zero-sequence component is null, and equation 91 can be written as follows. Then, by dividing by the base current, we obtain the dynamics in per-unit values. In equation 92, the current IDCS coming from the machine-side converter still needs to be determined. Two currents affect the DC voltage equilibrium. One current, denoted as IDCC, is the DC current extracted by the grid-side converter. The other, IDCS, is supplied by the machine-side converter. Finally, equation 95 represents the complete dynamics of the DC voltage. Note that the variables of the grid side and machine side converters are in their respective synchronous reference frames. As shown in the circuit of the average converter model, the internal converter voltages are related to the modulation indices in the stationary reference frame as expressed by equations 96 and 97. These equations are represented in their reference frames as shown here.
To conclude this section, we provide guidelines for selecting the voltage and capacitance of the DC link. When using space vector pulse width modulation or min-max common mode zero-sequence injection, the maximum peak line-to-line AC voltage that the converter can generate is equal to the DC voltage value. Therefore, according to our base voltage convention, the DC voltage must be equal to the square root of 3 multiplied by the base voltage. A dynamic margin alpha is usually adopted, resulting in the DC voltage value shown in equation 102. Regarding the DC capacitance value, we first define the capacitor time constant. This constant, which has units of seconds, is a measure of the capacitive energy per volt ampere. It is analogous to the inertia constant defined in mechanical system modeling. In power converter stations and wind turbines, the capacitor time constant ranges from 10 to 40 milliseconds. We can use the capacitor time constant to calculate the DC capacitance, as shown in equation 104. Here, we present a numerical example. Using the base power and base voltage from the provided wind turbine data and considering a dynamic margin of 25%, we find that the DC voltage and capacitance values obtained from equations 102 and 104 are very close to the values in reference 2.
Before explaining the wind turbine control system, we must complete the model by adding an AC grid. This lecture focuses on wind turbines. Modeling wind farm networks and power grids will be covered in a future presentation. For now, we will simply connect the wind turbine to a Thevenin equivalent of the grid. This table presents the nomenclature used in this section. Figure 26 shows the point of common coupling and the Thevenin equivalent. The current, denoted as IC prime, represents the current injected by the wind turbine into the point of common coupling. We added a small capacitance C0 and conductance G0 to model the bus voltage. We will describe two approaches for modeling the bus voltage. In the first approach, we consider the external line current IE and the voltage at the point of common coupling VH as dynamic states. By applying Kirchhoff's second law to the previous circuit, we obtain equations 105 and 106 in the alpha-beta reference frame. These equations are in complex notation and per unit. They model the dynamics of the external current and the voltage at the point of common coupling. Using the frequency translation described earlier, equations 105 and 106 can be written in the network DQ reference frame, as shown in equations 107 and 108.
In the second approach, we consider the external current as a dynamic state and the voltage at the point of common coupling as an algebraic state. To accomplish this, we set the capacitance in equation 108 to 0, resulting in equation 109. As discussed in the per-unit system section, the base power of the wind turbine and the AC grid are usually different. Therefore, we need to convert the wind turbine current from its base to the AC grid base using equation 110. Finally, the AC grid model used in this study is expressed in scalar form by separating the real and imaginary parts of equations 107 and 109. To conclude this section, we introduce the definitions of short circuit power and short circuit ratio. These terms are frequently used in power system modeling. We also illustrate power flow and losses in a permanent magnet synchronous generator wind turbine. Figure 27 helps identify the powers at different stages of power conversion. Additional losses, such as DC bus losses, were neglected in this study, but they can be modeled by adding a shunt resistance at the DC bus. In the next video, we will introduce the phase-locked loop and the control strategy for the converters. Thank you very much, and follow us for more content like this.